it off to Micah.
Great. Thank you, Jerry, and thanks for the opportunity to be here. I'm going to talk about an approach that we call AIMD EXAFS. So it's basically running first principles molecular dynamics to interpret X-ray absorption spectroscopy experiments. And I think I have to click this before I can advance my slides. Okay. Yeah, so this is an outline of what I'm going to talk about. I'm basically going to explain kind of our viewpoint, how we do the simulations, and why. And then I'll show a couple of examples from crystalline host materials, some examples from amorphous host materials. And then I have some kind of speculative content about information content in different spectroscopies that I'd like to show people and invite comments on. So this work comes out of the geochemistry group at Pacific Northwest National Lab. And so almost none of what I'm going to show you today is stuff that I've done. A lot of it is led by Eugene Ilton, who is here. But we're a geochemistry group at one of the national labs in the DOE system. And it's really an honor to be able to work at this location. It's a really kind of special group because we have world-class expertise and kind of a full loop of scientific inquiry where we can make nanoparticulate mineral materials that are the basis of characterization, and we have a whole zoo available to us. But kind of the real special thing about this group, which has been long running major geochemistry group that was led by Andy Felmy for a lot of years, and in recent decades has been run by Kevin Rosso. It's a long, stable program, and that's allowed them to develop a strong stable of computational theorists. And so it's really their work that I'm showing. Eric Bilaska and Sebastian Kiraset and Duo Song. It's a really synergistic environment where we've got everything here, and I think we do really good EXAFS in interpretation. And so a lot of what we're trying to do, I think, is get do what I call bridging the complexity gap. So a lot of typical idea of theory is that you need to compute some property of the material, like a bond length or something. I think a broader view is that like what you want to do is interpret the whole experiment. So the sample is an important part of that, but so is are the experimental parameters. And a lot of the interesting stuff, I think, happens when there's non-ideality. So it's not a perfect crystal, or it's happening not in the bulk, but at the surface. And in this talk, I'll focus a lot on impurities, which can affect things, provide a special site where a lot of special things happen. And so the reason we're doing our theory is to get scientific inference out of experimentations. And kind of the challenges we're up against are like, we can only make our models so big, and it's hard to directly interpret a calculation. And so I'll show you some ways that we've been successful in doing that. So I have this slide in here because throughout this talk, I'm going to say like, oh, you can't get this information from shell by shell fitting. And I'm going to point out the limitations of that. So I want to say in the front that the development of the point scattering theory of EXAFS and all the machinery that goes into extracting the fine structure and interpreting that in terms of structural parameters is really, it's a towering intellectual achievement. that's great, and it's where we start from. So I think what we call shell by shell fitting in EXAFS is really great. But what I would say is that it can be challenged when there's a lot of disorder. Shell by shell fitting works best in a well-ordered system where you have a well-constrained structural model, and then you can fit the parameters to high precision and get really good distances. But if you don't quite know what's going on, it can be tricky. And I guess the way we usually verbalize that is disorder makes it hard to use shell by shell fitting. So this is kind of our recipe. This is what we do. We use ab initio molecular dynamics, as I said, and the reason to do that is because we can faithfully simulate the thermal motion. So if we look at the structural disorder in materials, we can kind of divide that into thermal disorder, that's the vibrational motion of the atoms, and structural or compositional disorder, which is kind of the way things are arranged. And the vibrational disorder is almost always in equilibrium, right? It's thermal equilibrium at some temperature. You really can't get away from that. But the structural disorder is often, there's no equilibrium principle that tells you what you're going to find. Things can be trapped, and it depends on kind of the history of the sample. You just get what you get. There might be anything. But since the vibrational disorder is predictable, we can take that uncertainty out of the measurement by theoretically predicting it. So what we do is we look at a situation and come up with different plausible ways we think an impurity might be incorporated in a host material. So here I've got 6 different, what I would call incorporation motifs for a neodymium atom in calcite in this case. And then for each one of these things, we'll run a molecular dynamics trajectory to generate a theoretical standard. And then we use those theoretical standards in linear combination fitting. So this is kind of a generic approach. You could use it for a lot of different techniques, and I'm interested in kind of expanding it. But right now, we usually do EXAFS and PDF mostly. And by theoretically simulating the thermal motion, we can get a better look, I think, than normal EXAFS analysis at charge compensation mechanisms and the local structure around impurities. So kind of our powerhouse for doing this is we run a lot of DFT-based molecular dynamics, big, heavy computations. And I wanted to take this opportunity to really advertise what I feel like is an underappreciated asset of American science, which is the plane wave pseudopotential module in the NWChem package. NWChem is a quantum chemistry package that was developed at Pacific Northwest National Lab. And this guy, Eric Bilaska, if you know him, he's quite a character. He's one of the people that it's fun to work with. But he has hewn like a competitive plane wave DFT code just out of bare nature. I think he basically wrote the whole thing himself, and it's got tons of features, and we've used it to just run tons and tons of molecular dynamics. A lot of it using a hybrid functionals. And he's got some really interesting ideas that he's pursuing with Duo Song and Maria Shushko for interfacial reactivity that involve coupling density functional theory calculations with this classical density functional theory, which models like the chemical potential and electrostatic potential of the solution on top of a liquid-solid interface. So anyway, that's interesting. And this NWChem package is great. We also use it. I won't not talk about it today, but Neri Govind has developed TD-DFT methods in the Gaussian orbital part of this code that are good for simulating Zanes and valence to core XCS. We get a lot of that. And then from those trajectories, we just run FEF on it. And so I think that's nominally my role in the project, because I'm have the FEF expertise, but the FEF group has really been so good at making FEF user friendly that you don't really need any expertise to run it. But anyway, so those are the codes we use. Now I'll give a couple of examples of how this works out in practice. So like I say, in geochemistry, and the big things people are concerned with is how different elements move around the surface of the Earth. We call these cycling. And this iron, oxygen, hydrogen system is responsible for a lot of it because iron's really abundant. And so what'll happen is some trace element will get incorporated in iron minerals and then like move around that way. So we're interested in how these things get incorporated in the local structure, because that's what determines how that impurity changes the host phase properties. I'm going to have a few slides here on uranium. So you might want to sequester that, keep it from going anywhere, or to tailor the host for certain properties like photoabsorption or whatever. And so, of course, since EXAFS is element specific, you can look at the edge of the impurity. It's good. It doesn't get swamped out by like signal from the host. But as I pointed out, unless every impurity is incorporated exactly the same way, it can be difficult to interpret what the EXAFS means. And that was the case for uranium incorporated in hematite. There was kind of these competing publications in the literature. They all had their own data, and the data was more or less consistent, but the interpretations were all slightly different. And there was a difficulty getting scientific knowledge from the signal. And kind of a hallmark of this was that they all had these high Debye-Weller factors in their fits, and that was just an indication that disorder was hampering the interpretation. So when iron appears on the surface of the Earth, it usually forms an amorphous hydroxide solid that then transforms into this poorly crystalline phase called ferrihydrite. And then that, as it ages, changes into this mineral called goethite. And goethite's very common in the Earth's surface and can incorporate uranium. And so how is it stuck in there? One of the things that makes it tricky is that the uranium can adopt 3 probably reasonable charge states when it's incorporated, and it's not clear a priori which one it's going to have. The other is that all these charge states are higher than the iron 3 charge state in there. And so if you incorporate uranium by putting it on an iron site, you have to compensate that charge somehow to make the crystal chemistry work out, to make it charge balanced. And so the group at PNNL and collaborators investigated this system using that recipe that I described before, and developed AIMD trajectories of different incorporation modalities. And the really interesting thing they found is that you can distinguish the oxidation state using the EXAFS. The theoretical standards for uranium-4, uranium-5, and uranium-6 all look pretty different enough that you can fit linear combinations to match the data. So this is based on this really heavy calculation with you've got tens of picoseconds for tens of charge compensation schemes. Most of it run with hybrid density functional theory, molecular dynamics. So I think that's just a tour de force of like brute force numerical MD. But it had this big payoff in that it turns out when you do the linear combination fitting, the uranium, it likes to be incorporated largely as the 5+ charge state. And that was new knowledge. And the charge is balanced by taking out these protons from the crystallographic structure or adding electrons. And so if you look at those standards, they're averaged over a molecular dynamics trajectory. And in that trajectory, these protons will hop around, especially in the uranium-5 charge state. For uranium-6, they're not mobile. For uranium-4, they're maybe mobile, not very mobile. But in the uranium-5 charge state, on molecular dynamics timescales, these protons hop around, and that affects the EXAFS amplitude, and that's the mechanism by which the EXAFS amplitudes are affected by the oxidation state, right? The typical conventional wisdom is like, oh, you do Zanes to get oxidation state, you do EXAFS to get structural information. But so the point is, if you faithfully model that hopping motion, then you can get to like the true picture. But you kind of have to get both that dynamic disorder and just the fact that the proton moves around and is compensating the charge to explain the observed EXAFS. And so I think that kind of brings up a major challenge of applying these methods to EXAFS, and that's that you have to generate all these theoretical standards to fit to, right? And so a big thing is just positing the incorporation motif. And so there's some principles that you can do it. The big thing is relies on human chemical intuition at this point, I would say, and this is kind of where the art of applying this is. So if you think about how does a trace metal get incorporated in a crystalline host mineral, in alliovalent substitution, you have to balance the charge is the main thing, as I said, and usually if you need to put in negative charge, you can remove protons, you can remove metal cations, or you can add electrons. If it's like a divalent substitution in a trivalent mineral lattice, you do the opposite. You can use oxygen vacancies. And then the other kind of piece of wisdom that's emerged over the years, I think, is that the local symmetry around the impurity that you're putting in is important. That the impurity might want a preferred coordination number or symmetry around it. But really, this is I think the hard part of doing this. And then of course you have to run molecular dynamics on all those. But anyways, kind of that challenge that I started out when I showed the 3 experimental EXAFS that had published varying interpretations of. Here's kind of the resolution to that. So that this comes, we looked at goethite in the last slides, and I showed, you got the proton disorder. Goethite, when it ages, can dehydrate and form hematite, which is a corundum structure with iron. It's the kind of thermodynamic endpoint of oxide for iron. And so it turns out uranium can also sit in there. That was not necessarily known. And how it does, I think this is kind of a big conclusion of this type of work is this trans corner configuration is makes it possible to stick this in. And so what happens is the uranyl kind of in solution or out in the wild, uranium 6 likes to be found in this uranyl motif where it's got this 2 oxygens in a straight line, and it has these kind of short bonds, and there's not any good way to put this into the hematite lattice. And so what the hematite does is it forms a kind of row of 3 vacancies where the middle one is occupied by the uranium. So the uranium substitutes at a site that has 2 accommodating vacancies, and then protons fill in those vacancies, reminiscent of hydrohematite, where there's kind of some water in the lattice. And this was found by linear combination fitting of these molecular dynamics things. And so I think this is the same slide. But so you had these 3 competing interpretations, and then I think this work led by Martin McBrady and Eugene Hilton kind of established that this is what's really going on. It was shown on natural samples that uranium can stick in hematite for geologic times, like billions of years, and that the availability of these theoretical standards allowed fairly quantitative determination of the populations of these different things. And so for a while that was speculative, or maybe not necessarily definitively accepted that that's what was going on. And then I think this slide is here to remind me to say that follow-on work using electron microscopy saw basically the same thing. This was going to be my killer slide, where this is a movie where this is the hematite lattice, and some of the columns are bright, and those are ones that have uranium in them. And as this observation continues, these bright columns will shift occasionally on the time scale of this electron microscopy experiment, and they shift in a manner that's consistent with the MD simulations and the EXAFS fit. And so that was a great kind of confirmation that this and look at that, it moves. But anyway, that this way of interpreting the EXAFS had allowed us to figure out how the uranium sits in hematite, and also explained how it sits differently in hematite than in goethite. So it's like often 6+ in here. Those competing interpretations of how how uranium was incorporated in hematite varied a lot in the fractions that were assumed to be absorbed on the surface as uranyl and incorporated as uranate. But this kind of microscopic picture with the protonated iron vacancies kind of resolved that dispute and allowed the interpretation that a uranyl light signal could come from the bulk. And it also showed why uranium can be 6+ in hematite, but is almost is usually 5+ in goethite. So that's kind of the kind of geochemical information that we're after and that you can get if you're good at doing AIMD EXAFS. So that was a, a, a case where the defect was higher charge than the substituent was higher charge than the normal lattice cation. The geochemistry group has also looked at divalent substituents into these iron minerals. And so like nickel and zinc are common transition metals. And so we have the same kind of questions. Here, the kind of science questions focus on how does the presence of nickel and zinc affect the host, and kind of the background or maybe the punchline is that there's a different observed solubility reactivity or stability depending on nickel and zinc. And so, like I said, in this group that I'm privileged to work on and their collaborators, there's a great we can target experiments to check these out and target the calculations to match them. And so they co-precipitated made some ferrihydride in the presence of nickel and zinc, and then aged that to goethite, and there was parallel molecular dynamics done, just like I described before for the uranium. And again, they were able to generate many configurations theoretically, and then down select and figure out which one of those actually occur in these kind of definitive fits. And so you get pretty quantitative speciation. And the takeaway is that because of chemical differences between zinc and nickel, the zinc has charge compensating protons, and also iron vacancies, but the nickel doesn't pull in any vacancies. And so that affects the structural energetics. And so it see if I can get through. And the vacancies allow the relaxation of this stress energy, and that's a major determinant on the stability of the goethite that's precipitated with those elements. So that's a second example of how this can be used to identify how trace elements are incorporated in crystalline hosts. And so that brings me to my first question slide.
Thanks, Micah. That's a lot. That's a lot of really interesting stuff. We'll start with Fairvila. Fair?
Yes, just give me a second. I was turning on the video so Micah can see me, because since I can see him. First of all, it's so weird to see you with short hair. That's number one. So I actually have a couple of questions, and I'm just going to launch them all at once. So first of all, the motion of the protons, it's in my experience is very quantum, but I assume you're doing classical AIMD. So how do you deal with that? On a related note, a lot of the bonds that you're dealing with are pretty stiff. All the uranium-oxygen bond in UO2, it is a very stiff bond. So I would assume that it is very much at a 0-point motion at the temperatures that you guys are doing simulation. So that is actually going to be affected by quantum effects too. So those are my first two questions. I have a few others, but those can probably wait. I mean, that's the main interest one. It's how do you deal with quantum effects when you're doing classical AIMD?
So I mean yeah, all the MD is room temperature, and you would have to, to compare to experiment at any other temperature, you'd have to do it there. You're right that all the protons are purely classical, and we don't account for any quantum effects or 0 point motion. I don't know how large those would be. It likely, so quantum effects could like lower the barrier for this hopping or change the frequency between these two. But I think the important thing for determining the EXAFS is kind of how much it's on this side of the tunnel and how much it's on that side of the tunnel, and maybe how much it's in the middle. So I think in EXAFS we're kind of okay because like the hydrogen doesn't scatter the X-rays very much, right? It's kind of like a secondary effect, and so as long as you capture that, fine. But yeah, it's definitely a shortcoming of the method.
And I have one more. Can I ask it, Jerry, or do you have more people lined up?
We have more people lined up, but
Okay.
Be brief is what I'll say.
Okay, I'll be brief. So one of the issues with using DFT structures, because that's what you're doing. You're using AIMD structures to fit, in essence, the EXAFS, implies that the structures that you're getting from the DFT are as good as the one from the EXAFS. But in my experience, they tend not to be. So it's actually very hard to fit an experimental EXAFS using theoretical structures. So does this imply that the hybrids that you're using are actually giving you extremely good structures? Or are you doing something that basically allows you to fit even with poor structures?
Well, I think it's a matter of precision. So when the structure is disordered, if you look at these fits, we publish the best fit we get, but they're still not perfect. And so if it was a nice crystal, this might not be considered a great fit. And kind of the level of DFT error is kind of that order, right? So the DFT errors are still there. We can just get away with it as kind of a lower fidelity application.
So as long as the centroid is basically correct of the distribution, you're fine. So I'll mute myself, Jerry. Bye.
Very good.
Nice to see you
Matthew,
here.
Yeah.
Matthew, you had a question?
Yes, actually, on Fernando's point, yeah, I found that in DFT there's always often an error of scale of distances. Do you adjust for that?
No, these are in NPT molecular dynamics simulations. So I do think like throwing the temperature in helps, but the other thing is this is EXAFS of a point substituent in a bigger crystal. So sure, the hematite lattice parameter may be off by 1%.
I see.
Or something, but it's the local structure around the uranium that we're really probing, right?
Yeah, and also I was wondering how the hydrogen, how the protons affect the EXAFS, since as you pointed out, they don't scatter. Is it because they change the positions of the other atoms?
Yeah, it's the interplay between these protons hopping around. In this case, they don't always, but they're still important because they'll change the bond lengths and bond angles by changing like a bridging oxygen to hydroxide group. That kind of just around the impurity again, right? It's a local effect.
And if I may be permitted a third question.
Really fast, please, because he's down to probably about 20 minutes left.
Okay, maybe I'll defer to the second break or the end.
Okay, very good. Micah, you've got about 20 minutes left in the regularly scheduled time, and I'll let you strategize as you see fit.
Okay. Let me see. You were right to warn me about this slow because I'm having trouble getting to. Yeah. Okay. Well, so I'll kind of shift gears and give another quick example where AIMD is useful. And that's basically to simulate both EXAFS and PDF from the same common model. So this part of the talk is going to focus on carbonate minerals. And I just wanted to put this slide up here because out of all these curves, there's almost zero adjustable parameters. These are all crystalline polymorphs of calcium carbonate. Except maybe for this, no, that's calcite. Okay, yeah, and so these are total scattering or pair distribution function measurements. It's an elastic X-ray scattering technique, but from molecular dynamics trajectories of the crystalline polymorphs, all these amplitudes are, just forward computed. It's a pure prediction. And so this is a good tool for simulating PDFs, I'd say. And then we can since we know that it's good at getting the PDF, we can use it for amorphous systems. And so amorphous calcium carbonate's it's a widely studied system because it's used in biological systems a lot. And it's a really flexible material where you can make a lot of different crystalline end members. And those crystalline end members are formed through phase transformation changes that go through amorphous phases. And so how does that work? Well, to understand that, you have to understand the amorphous phase. And so we've done a lot of simulations of amorphous calcium carbonates and compared them to PDF and EXAFS measurements. And I think the take-home messages are that using these molecular amorphous models, we can really get a lot of insight into the content of the different peaks in the PDF. That's surprisingly hard to get just from a naive interpretation. And they give us these trajectories that faithfully reproduce the PDF and the EXAFS. So a common way of interpreting a PDF measurement is to use this method called reverse Monte Carlo, where you take a big box and you kind of move the atoms around until the PDF matches. But I think we think our theoretical structures are better because if you use the structures generated by reverse Monte Carlo or by classical MD, they don't do as well on the EXAFS, even if they match the PDF well. And so this is a flow chart of how we use AIMD to model amorphous structures. And it's not something we invented. It's a classical way of doing it. It's just melt quench, where we randomly we take a box, we put in calcium and carbonate groups, we run some classical molecular dynamics to get it good. Then we run high temperature MD for 16 picoseconds using the DFT. And that generates this molten bath where all the atoms have been randomized in position. And then periodically we'll pull out a structure from that molten bath and quench it down, and it freezes in a disordered amorphous structure. And then we run room temperature MD on that and extract a thermal ensemble of structures, just like we did for the crystals. And I think it works really well. The agreement with the total PDF is not as great as with the crystals, and so there's still kind of tons of open questions about what's really going on. in there, but we identify kind of all the distances really well. But I think the really powerful thing is that it's really good at identifying changes with composition. So in this case, we're looking at hydration level. So when the ACC, the amorphous calcium carbonate forms, it's usually hydrated, has some water in it, and all of the crystalline end members are anhydrous, and so that water has to get out. And the way that dehydration works is thought to be one way that you can control what kind of crystalline product you get. And so it's studied a lot. And one of the main things that changes when you change the hydration level is this peak, which is the main metal oxygen peak, right? It's this arises from scattering off of calcium and oxygen distances. And so most of the naive interpretations in these works were like, oh, this must have something to do with the water changing the calcium oxygen interaction. But by running models with different hydration levels and then looking at the differential PDF we predicted from there, we were actually able to show that even though this peak is mostly the metal oxygen peak, the changes arise from changes in the, I think I might have one more slide on this, yeah. Changes in hydrogen bonding between the waters and the carbonates. And it's just that those distances happen to overlap, and so it looks like a peak shift in the calcium oxygen distance. And that's the kind of thing that would be really difficult to understand without a good atomistic model. And so we were able to use AIMD to do that, and I thought that was good. And then another example is that we can actually look at impurities incorporated in ACC. And so we do basically the same thing we did for the crystals. And we run a bunch of MD with zinc in there. And in the MD, we see the zinc likes to be fourfold coordinated, and it dissociates a lot of water. So it's a pure theoretical prediction. So that was kind of cool. We went out, looked for it. We precipitated some ACC with zinc in it. We collected EXAFS of that sample in a laboratory-based X-ray spectrometer, and we did shell-by-shell fitting on that, and also just straightforward prediction from the MD. We get the same answer, and so it is, I think, pretty conclusively true that the zinc is much less coordinated in ACC than other divalent species. And so that was a kind of a theoretical prediction using AIMD that would be hard to make other ways. And so this is my second slide. I can skip this and finish with a couple of quick slides, and then.
That sounds good. Keep going. We have a couple of questions. We'll hold those for the very end.
Yeah. So the last thing I just kind of want to throw out in front of the community, I'd be interested in any thoughts people have, is kind of how to deal with this multimodal fitting, and I'll explain why this is a question that I have. So we normally think that ZANES measures the electronic structure, EXAFS measures the atomic structure. I've shown some ways that that's not exactly true, but there's this basic problem that there's no EXAFS equation for the ZANES. But maybe I'll do these in a different order. using these data sets, we have all this MD and all these X-ray absorption simulations based on those trajectories. And so we were messing around with some, machine learning algorithms. What can we do with that? And we made this interesting observation, at least I find perplexing observation, that given a PHEF calculation of the zanes for zinc incorporated in hematite, we can train a neural network that will predict the EXAFS of that. And from a theoretical point of view, that's just a weird thing, because the kind of what you would put into a calculation of the zanes and what you put into a calculation of the EXAFS are different, right? They're totally different regimes of photoelectron energy. But I mean, we tested this pretty thoroughly, and it's a real effect. It's not some kind of like quirk of the data or anything. But using synthetic data, we can train a neural network to predict the zanes from the EXAFS. And so I have this idea that well, that means that the structural information must be totally encoded in the zanes, right? At least to the level that you could do a fit with the machine learning predicted EXAFS to extract those structural parameters. And so I'm looking for a way to get that structural information out of the zanes, but not just the zanes. I think that this kind of neural network that relates one mode of spectroscopy to another spectroscopy could be useful for rationalizing multimodal data sets. So I just wanted to throw that out and see if anyone in the audience had any ideas or comments. So I think I'll stop there. Thank you.
That was very nice, Micah. Thank you. We'll start off the questions with Molly.
Hi, can you hear me?
I can.
Yeah, thank you. Thank you for your fantastic talk, very educative. You had mentioned that the RMC of the PDF data was not as good, but if you were to include EXAFS in the RMC, would you expect the information content to be increased and therefore be comparable to the approach that is taken with the MD approach that you have just shared?
Yeah, that seems reasonable to me, and I didn't, I didn't mean to discount the RMC methods. I think that's a great, way to find a structure that fits the data. And yeah, obviously, I think if you use the EXAFS in the RMC fit, and I think that's been done. I'm not as up on that literature as I could be, but yeah.
Yeah, thank you.
I have a question. You didn't talk a lot. You showed the molecular dynamics simulations and how it could help you with directly predicting the EXAFS. This was much earlier in the talk. Don't flip slides or anything. It's all good. What you didn't talk about was comparing what you get when you have the molecular dynamics and you're actually looking at the proton hopping to instead doing the traditional cumulant expansion for Debye-Waller. Any comments on that?
Yeah, I didn't show a good comparison. I think what happens in these situations where there's multiple ways that an impurity can sit in a host is that, I mean, what you see is the overlap of those. And then the kind of the best you can do because of like the Nyquist criteria or whatever is fit a single set of shells, right? Like a first shell and maybe a second shell. And that all the disorder, whether it's thermal or configurational, then goes into a Debye-Waller factor. So obviously, like describing the proton hops with the cumulant, you'd have to go to really high order. Like that's not a reasonable way to go, right? What does Fernando say?
Yeah, go ahead, Fair.
Oh no, I mean, actually, I had a follow-up, so no, continue with that, and I'll ask my question.
I think
Yeah.
he's explained it to me sufficiently at the level that I know how to use cumulant analysis. So you should go ahead, Fair.
Okay, so no, the question I have is, I mean, for this last part of the talk. So I'm curious as to how much of the sanes I mean, or the energy range in the sanes you included in the training, because I mean, the EXAFS really it feeds into the sanes quite a bit of information. So if you have enough energy range in the sanes that you're using for the training, you might actually have enough information to actually predict large swaths of the EXAFS in K range, right? So I'm just wondering, so you're going to K equal like 4?
Yeah, and more. It's like 5. But
5. So
yeah, we do think we can do it with less, like up to 4, but not just the pre-edge or something like that. So
okay,
this blue line is where the Zanes ends in K. So this was like seen in the Zanes, but it was seen as mu, not as chi, right?
okay, yeah.
And then all that's predicted.
Okay, so then maybe you're getting such good agreement because you have enough information. You're capturing enough information out of the saints, really. I mean, enough structural information is in there. But by the way, I mean, in my experience, the division of like electronic structure versus like structure in saints and EXAFS is completely arbitrary. I mean, the electronic structure is completely dependent on the actual atomic structure that you have in there. So it is encoded in it. It's just that it's a little bit harder to separate because it's not a one-to-one equation that you can use, but it's there. So I'm not really surprised that you're actually getting it well. It's beautiful, right? I mean, that actually you're actually able to do it. But yeah.
Yeah,
Anyway.
I wish we could do it with experimental data.
Yes, I know. Yeah.
We're almost out of time. I'm going to ask the last question. So it's really interesting that you're able to use the extended EXAFS to infer the Zanes. And it's the first time I've seen the machine learning go in that direction, right? So much of the work on machine learning in catalysis, for example, is on inferring structural parameters from the Zanes only. Um, any thoughts on what you're doing? Would it have value in other fields? What they're doing? Could it guide where you want to go?
Yeah, well, so kind of our idea was that, well, there's a lot of situations where it's hard to get a high quality EXAFS, right? If the species you're looking at is low concentration or it's an in situ experiment or something. So if there was some way that we could get decent signal to noise out to a moderate K, could we extend that spectrum up to higher K and then do normal EXAFS analysis on the spectrum? That was kind of the motivation for it. And also just that it was kind of a different tack that nobody that we knew of had tried. But yeah, I think the usefulness of this is to maybe take a lot of not bad data sets, but data sets that are limited by signal to noise and combine them into one information package. I think neural nets are good for relating between the spectroscopies. I'm not quite sure how to do that, but you have like high signal to noise XAS, high signal to noise infrared, high signal to noise EELs. Can you put that all together and get one good experiment out of it? Or one good interpretation.
Got it. I understand. With that, we're close enough to out of time that I'm going to thank the speaker and thank everyone for coming. And I'll stop the recording and then we can chat informally for a few minutes.